Okay. Hello everyone. So today we will continue our discussion on boosting by looking at what's called gradient booster. The most famous application of gradient boosting is for what are called regression trees. Sorry. So yeah, so that's the ultimate target we're building towards. So this is called gradient boosted trees. Yeah, GPT. I will not go into the gradient boosted trees in great detail today. That we will do next time. But today I want to just cover what gradient boosting is and what the principle is. Like, why would anyone think of something like this? So yeah, so today, so yeah, what is gradient boosting? And yeah, and why of it? And I will tell you what a regression tree is. What is a regression tree? Yeah, and yeah, why it is a good thing to do. And then yeah, next class we will kind of combine these two and tell you how to do gradient boosting for regression tree. So okay, so let's get started. So today will be like a lightweight class. Saturday also we don't want to be heavy. So the easy stuff and I'll do very slowly. Okay, so okay, so let's think of very basic. So here is the setup again, like just like last time. So you have xi, yi gives training data. And you can also imagine that this is coming from some distribution, coming from some distribution which is not really relevant right now, but yeah, there's something out there. And yeah, and you have again, you go to learn a function which maps x to y. So so you want to like learn mapping f. Yeah, so that's a big picture, and possibly you want to learn the optimum mapping. So let's call it f star. So yeah, so what do you want to learn? So you want to learn f star, which is the r min over some function, so f in some class, capital F of yeah okay. In fact, I don't have to use the capital F at this point right now. It will just literally all f's, the expectation of the true distribution. So by x, maybe some loss by. Okay, so this is setting expectation. I don't really need to limit myself to a class, right? I can just look at everything. Expectation covers all points. So yeah. And so yeah, so I will just figure out what this mapping is, and so that's the starting point, and now yeah. So since you only have a restrained data, you would have different data. So we have limited data. You don't want to overfit, and that's why you want to restrict f to a parameterized class. Restrict to some parameterized class. So you want to call it as f of input and some parameter. Yeah, a piece of vector of parameters. Yeah, and yeah, and now if you remember last time, so just to like put things on the ground. So in the boosting way of thinking, these functions look like sums of functions which you have built up step by step. So if you remember last time, at every step I would pick what we called a weak learner or weak classifier, and then we added it to our function. So the function can be expressed as a sum of functions which we can build like this. So yeah, so that's what this looks like. So for x, yeah, so of beta m. So beta m is your coefficient, your weight to the function at the mth step, how much weight you're giving, and you have some some parameter vector which will define the function at the mth step. So yeah, so now this is sum, right? So at every step, I will take a weight, a beta m, which is like learning rate or weight or something, and then I will have this base function, classifier or regressor or whatever you want to call it. Okay. So yeah, this is what it looks like. Okay. Okay. So now, in ADA boost, which we covered last time, we work with exponential losses. So we measured our so in particular, if our a class label predicted on a particular data point went wrong, then we change the weight of that data point by exponential amount. Right? So the loss function used to learn the h there was exponential. Yeah, in some sense. Okay. So yeah, in particular, it was exponential, but also a bit more generally. It had a structure that the loss was a function of which were functions of y times f. Okay. So you could express it as a product of the true label y, so true label, and the prediction f, or maybe h in this case. No, okay, yeah, f I guess, yeah, and f. So if we recall, since our labels were +1 -1. If YF was 1, it means that I'm predicting correctly. If it's -1, I'm predicting wrongly. The loss depended only on this product. So yeah, so you don't have to know Y and F separately. You only need the product. Yeah, and somehow all of this nice structure, exponential and YF, it allowed us this nice algorithm. So allowed this nice algorithm. Yeah. But then, as you might imagine, in other settings, when your loss could be something different. Yeah, so maybe we want to do something in a much more general setting. So so in that setting, the classification, it makes sense to do it like that. In another setting, there is such not classification, and we're trying to do maybe regression with a more complicated. Yeah, but what if you want to do regression? You want to do regression with like complicated models. Okay, I think at the end of the last class we also looked at regression with linear models, but maybe you don't have linear models. You have something much more messy with more complex models. Yeah. So then all of this nice structure you had kind of goes away, and then you want some way of doing boosting, which is more general. So yeah, that is the motivation for gradient boosting. So yeah, let's build towards it. Okay, good. So okay, so yeah, let's first start with a very idealized world. Okay. So idealized. So you start with idealized world, and we make it less and less ideal as we go along. So let's say uh, you want to, you can actually work with the expectation. Okay. So of course you can't do that. You can only work with finite data points. But suppose you could work with expectation. Yeah. Then what kind of algorithm for boosting could you come up with? So let's think about it. So let's see. So let's say uh, you have your current function or maybe parameters, right? And yeah, and then you want to update your parameters. Want to update on the parameters. So this is what happened in boosting, right? At every step, I had accumulated some parameters by, at every step, I had fit some base classifier, I had accumulated some parameters, I had obtained a function. Then I want to update these parameters by introducing a new function. So yeah, I want to increase my parameters. Yeah, that's what was going on. So yeah, so at a very high level, what might one want to do? So yeah, so very roughly speaking, so this is like very rough because it assumes a lot. So this I'm trying to get the picture. So very roughly speaking. So what you want to do is that you would want to maybe find a gradient. So you want to find at step n, you want to find the gradient gm, which is the so literally find the partial derivative of your loss. So loss looks something like so when you take the expectation, remember, suppose I can work with expectation, so everything is idealized. So I can work with expectation of the loss. So I take this expectation of the loss as a function of the parameters. I take the partial derivative, and yeah, so partial derivative with respect to the jth parameter. Okay. And I compute this at the current parameter. So p equal to the current parameter. Okay. That's the gradient. And then just do update. Okay. Then I find then my I update PM. So PM is my old parameter plus some PM. Yeah, my update at the end step. And this update looks like, from your old understanding, it looks like something like minus some learning rate rho m times the gradient. So I move some step in the direction of negative gradient. Okay, this is what we have always done in life. And yeah, and how do you set rho m? So I guess you set it in multiple ways. So one is that you can take something constant, but something more intelligent, which often people do and it works well in practice, is what's called line search or sequence descent. So I want to just mention that. So So blind search steepest descent. Yeah, okay. So I like line search better because I think that really indicates more what's going on. So this is just saying that you so you update. So rho m is, so this learning rate rho m is arg min over rho of this. Okay, let's call this phi. So just call this phi. I'm going to try it again. It's phi of p. Okay. So phi of, so you take your current parameters and you look at the update. Okay, there's no parameter GM. Okay. So apparent for line search, because essentially, I am trying to find the best point on the line. So if I think of this as my PM -1, and I look at this line passing through PM -1, its slope or direction is -GM. And I want to see how far I should go on this line. So I should go rho amount from this line. This one is called line search. Okay, so yeah, so this is something which people would have liked to do in an ideal world. And okay, so now let's make things a little less ideal. Okay, so to do that, let's change our view a little bit. So let's take a different view of the same thing. So different view. Okay, so so right now, since we are still thinking ideally, I mean maybe a bit less ideally, but still ideally, we're still thinking that we have access to the expectation. So if we have access to expectation, then another thing I could do is try to just directly optimize in the function space. So I mean, we need to go to the parameters because we are afraid of overfitting. But suppose we were not afraid of that. We are fitting fearlessly. Then I can just optimize in function space. Okay. So more specifically, what I would do is, instead of trying to build the parameter step by step, I would build the function step by step. And that's really what happens in boosting. We build the function step by step. So we say that my function f star, sum of functions which I built step by step. So you see the difference, right? So in the previous version, we were doing the most classic thing. We were doing an update to the parameters. Here I'm not updating the parameters. Yeah, I mean I'm updating, but in a different way. I'm kind of expanding the space more directly. So I'm literally thinking of f star as a sum of different functions. And yeah, and now okay, yeah. So now if I take the same view again, okay, so I want to again think of some phi, and I'm trying to again do some gradient step on the phi, but I want to do it in this way. So now I want to think of this little f m as a gradient update. So I want to pretend that f little m is great. Yeah, it's not gradient update clearly at the moment, but that's what I would like to interpret it. So how do I do that? How do I get there? Okay, so let's write down some things. So let's write down the function for which I should be finding the gradient. So the function should look like phi of f of x is expectation over by L loss of y to f of x condition on x. So actually given x, this is the loss which I'm suffering. And and now I want to say that my gradient should something be like gm. At any given point x, what kind of an update would I like to do? I would like to find the gradient of this function of phi f of x. So this is the partial derivative of phi f of x with respect to f of x, because that's what I'm trying to find, right? So x is the input now. F of x is what I'm trying to learn. So f of x is my parameter in a sense. So find the partial derivative with respect to f of x at my current iteration, f of x f m minus 1 f x. So already picked m minus 1 functions, and whatever value that gives me at x, I want to evaluate the partial derivative at that point. Yeah. Okay. And then I want to say that again as before, little f m of x, my update now, my new function should be this gradient, right? That's what we were trying to do. It should be minus the rho m, again learning rate, which I do in the same way, times this gm. So yeah, so okay, we can't actually do any of this because this is an infinite space. So
also the partial derivative would be in a different space, right?
So again, all of that has to be it's infinite space now, so it's no longer so simple. But I think here you're still okay, because again by isomorphism, it's a survive because
something not what space. What's the problem?
No, there isn't. I don't think there's a problem. I think. I mean, you could still do it like this, right? I mean, if you had access to, if you could compute in infinite dimensions, in uncountably infinite dimensions, then you could have done this.
I
mean, the partial derivative is just a real number, right? So it's all numbers. There's no trick here. I guess what you're saying is that I've not properly defined what a norm is, and because this is an uncountably infinite vector, and it should could arise if you were to good property, but I don't see an issue right now. I think it should go through.
But in implementation, we never expectation is finite.
Exactly. So right now this is idealized world. Okay, so now this is actually getting implemented. Yeah. Okay. So since now let's try to get to the implementation bit. So how would one go from here? Okay, so now in the finite world, now as you said, you can't actually do any of this, and you take a finite sum. But if you take a finite sum, then there's a danger that you will just overfit. So you should not do this. Okay. So now let's come to the real world, finite world, finite data world. Okay. So now I kind of want to do the best of both worlds. So I want two things to happen. So I still wanted to do some boosting like thing. So I mean, I like the idealized function way of thinking. So I still want to do this. I still want that my function fn should be sum of these functions. I mean, your function f should be the sum of my real functions. Yeah, I still want this to happen. And I want to learn these functions one by one, and I still want fm to be some gradient kind of a thing. So yeah, still want fm to look like a gradient. Yeah. So yeah, I still dream of this, but of course now it's not possible anymore, because if I do that, then I'm just overfitting. So also want to avoid overfitting. Okay, fine. And to avoid overfitting, the only way I know is to restrict my class of little fms. So I want to use parameterization. On the little fms. Okay. So like I said before, I'm going to write that I want my little fm to be some edge of some x and some parameters here. So I want fm to be some edge of x and yeah. Okay, so now how do I get both of these things? Yeah, that's the question. Okay, so any ideas? Maybe now that I set it up like this, maybe you guys can tell me how to do this. How will I get both of these good things?
What's the expectation you take them
Yeah, I mean, of course, that I have to do. There's no getting around that. So let's try that first. Okay, so okay, so here's the hope. So now I want to learn these parameters am. So I want to say that you want to find argument over beta m am. So let's call it. I'm putting prime here just to say that these are variables. I mean, I'm going to take minimum over these primes, and it's going to spit out the unprimed stuff. So so take all possible combinations of these parameters, and now you take the empirical thinking, right? So no, this is not an answer there. So now you have capital N data points. yi beta prime of xi am. Yeah, the same thing as before, but just the empirical version. And yeah, so in a slightly less ideal world, I would love to do this. Yeah. And what boosting tries to do is to do this in a greedy way. So instead of trying to optimize over these capital M different parameter vectors, I build these capital M one by one to solve. So yeah. So boosting way of thinking is boosting thinking says build these AMs one by one. Okay. So more specifically, what I really doesn't want to do. So let's write down. So at any iteration, how do I find my beta and am? So remember, I'm trying to find two things. One is how much of a step do I take, and what parameter do I use? That is well, okay. So it's just the min, what beta and a. So I take this thing which is written above. It's actually the same thing, but now I just say, okay, I look at the function constructed so far. So even most of it is called fm. So fm minus 1 at xi plus this change h x I. Okay, so yeah, that's the goal. And yeah, and now I just update my fm. So fm x is now fm minus 1 x plus. Okay. Yeah. Okay, so that's the boosting of thinking. Correct. The only issue here is that how will we even do this minimization? Because minimization is our lots of parameters, right? It's no longer a single parameter. So you have this entire vector of a bar, and this edge could be built in a very complicated fashion. So I think in the last class we looked at some simple classes of this. So like I mentioned earlier, yeah, in the last class we looked at settings where the loss looks nice. So if loss of YF is like exponential of minus YF. Yeah. So that leads to the RW boost from last time. And we also looked at this other thing called forward stage wise regression. But there, these edges were very simple. They were all, everything was linear and nice. Edge were linear. Yeah. So this is what we did last time. Okay, I think yeah. So this stuff which had been seen before. This RW boost. This is some forward stage wise. Yeah. Regression. Not okay. I don't think it's probably not exactly the same algorithm, but you can get something like that algorithm if you do this. Yeah, it's similar to that. Let me not say it's the same because it's not exactly the same. It's similar to. I mean, it is the same principle. Okay, but the point is that what I said last time worked when the loss looks simple and or the edge looks simple. But what if loss is like really messy? Maybe loss is some cost entropy, or something weird, or square loss and all kinds of stuff, and maybe your edge is also really messy. Yeah, then you can't do all of those things. Okay, yeah, but now, okay, this is what I said. Okay, what is the solution now? Okay, now what's so remember, I want to get those things on the top, those two things. So I want that this little fm, this edge that I pick, should look something like a gradient.
Right. Take the gradient of the loss function in the second line. So you have L of yi and
Yeah, fine. Yeah. There's a gradient. That's okay. That's all right. Then
if you pick beta not to last, then
but I also want that it should come from some parameterization, right? So how will I import that? So there are two things which
is the parameters. So
I think that sorry. No. Okay. So I think what I'm trying to say is that I want two things to happen. So I want my update here to lie in a parameterized class. So I want that my update should look like Peter times h of x times and parameters. And And I also want to find the best such update. So how can I do that?
So one way you can do that is you can take the gradient with respect to the parameter by using the chain rule.
Oh,
The other one is you
Yeah.
take the gradient and then you project it onto your.
yeah, exactly. So second is easier. Much easier because you need to project and okay, because chain will be easy when your edge looks nice.
Yeah.
But if it's like extremely messy, like it will look in a few minutes for trees, then you can't do such things. So yeah, then you do what you just said. So yeah, that is the great missing algorithm. Okay, so let's step back a bit and figure out what's going on. So yeah, okay, so then let's find the partial derivative. Let's find the gradient first. So yeah, a negative gradient at a data point, which is minus. Yeah. Okay, good. So now at every train point, I have this value. That this that have this vector minus gm. And now I do something similar to what Manor said. So now I will do the simple thing. Simple, but maybe not completely obvious thing. Simple idea is to pick the edge yeah. Yeah. So you pick that function for which the vector h xi n is most parallel to minus gn. Okay. I guess this is what we're trying to say. Take the gradient and then you essentially you project. So you figure out the nearest point. Yeah, and here the nearest means this, right? You want to match the director. So this is what you want. So yeah, and typically people are even more lazy. They just do like a least squares thing. So the so one suggestion which people do in practice is to just do these squares. So take the gradient value, the minus gradient value. You take the value obtained by making your update, and you want it to be as small as possible. And and in the sum of squares. Yeah, so that's like the most stupid way of doing it. Yeah. Yeah. So yeah. So this is quite literally the projection. Yeah. What it is. Great. And okay, so I think now we're ready to state the algorithm. So let's do that. So we'll put the complete algorithm now. With all this picture. So here is the gradient. Okay, so let's again recall what the setup was. So we initialize my function first. So yeah, so here's like a way of initializing. So f0 of x is so it's like a read dummy initialization. So I literally pick this one parameter, right, for everything. So it's like read dummy initialization. Now this is like constant function, right? Literally constant.
Right.
Yeah. Constant initialization. Okay. And then I say, then I do my iteration. So for little m running from 1 to capital M, we do the following steps. So you say that, okay, so you, yeah, so I want to find these, gradients. So let's call them yi hat. I don't know why I'm calling them. I think I'm just using the terminology of Greenman. So this minus. Yeah, I don't know. And that's why I really find terminology. Let's call it. Yeah, I just call it like GMI minus GMI. Say minus 1. Okay, and do this for all data points. And then I figure out the best fit of parameters in the least square sense to this gradient.
Beta.
Sorry.
So you're fitting both beta and AM.
Yeah, of course. Yeah, beta and AM. Yes. Beta and AM is spare. This is argument, and beta and AM. But actually, we will do it in 2 steps. So we will. Okay, so I guess okay, I think it's okay to do this, but you see what I mean. So okay, so at first, okay, let me first write down, and then see what this is. So AM, so argument A beta. 1 to n. Y, no, not y, sorry, it's minus 12. GMI minus beta H xi r. Okay. Okay. And yeah, I want to do this. So Saju, there are these 2 things here. I don't want to like confuse them. So there is one beta parameter here, which is used for matching up to the gradient. But once I do that, then I want to do a line search. And that's I want to find my weight in the actual function. So here I'm just finding.
For this one, you're matching it to the gradient, but then when you choose the actual beta, you will use the actual function.
Yeah, exactly. Yeah, so I want to kind of use the line search element also. So I think this is just trying to make my edge as parallel in some sense to the negative gradient. And this beta is just used.
From here only, it's like you're doing the line search on not L, but on like the linear progression to L.
Yeah. And I think just because my edge values are like on different scale, right? And beta is just to match the scale to the gradient scale. Yeah, that's why I'm not writing the beta on the left. But now we'll do the actual line search to figure out the real coefficient. The coefficient in the actual grade. So row m is now, there's a line search over row. Good. Okay. Yeah, and now I can do my update. Yeah, so that is my final algorithm. Maybe stay at it for a minute. Digest it. Okay, good. Okay, so now let's take some examples. Okay, so this is probably the easy examples. So example one is least squares regression. Okay. So yeah, so that's like the most basic of everything. And it's good to see what happens here. So now your loss is y minus f square. Okay. And I'll divide by 2 because I want to make the gradient look easy. So okay. And so yeah, so this is the loss. Then what is the partial derivative in that step? So now, okay, so let's go back to sorry again. So sorry. Yeah, so it is y minus f, right? So now the so
GM will be y minus f minus 1.
yeah, exactly.
Minus.
There should be a minus here. Yeah, exactly. Good. Okay. And okay, so what is the algorithm now? So now my update actually. Okay, so I think it's go back to this. The GM is this y minus f minus 1. So now the thing notice is that my AM bar and rho m, the two steps are actually the same thing now. Because it's square, right? So it doesn't really matter.
Yeah, because it's limited.
Yeah. So yeah, so again, combine it into one. Okay, so again, I combine the AM estimation and line search in one step due to the matching form. So they're the same form, matching form of the square loss for both. Okay. And yeah, and therefore, I can just do it in one line. Yes. Argument. So is xi minus rho h xi. Okay. Yeah, so that's what this looks like. Let's try this for a minute. Okay, the same thing, just that I can now combine it into.
This will be minus GM minus that, right? Or is it GM minus?
Oh, yeah, sorry. There's a. So, okay, wait, hang on. So it should be. So, yeah, yes, minus GM minus that. Okay, good. Yeah, of course. So it should be, yeah, there's a minus sign here. Good, thanks. Okay, cool. So, yeah, that's all it is. Okay, so now let's do like other more tricky functions. Example 2. So it's called the least absolute deviation. LAD. Question. So now you take the loss. Yeah, absolute value of phi minus f. Okay, and now let's see what my gradient is. Okay, so what is the gradient? So this is partial derivative. I sorry, respect to right, evaluated that. So what is this now? It's easy. So the function graph is like this. Yeah, exactly. This is the minus sign. And so they're right in one line. So minus b and I is the plus sign. Good. Yeah. Okay. So okay. So now what algorithm did you obtain now? So let's see. So okay, so remember. Okay. So how do you find the a now? So I want to. Okay. So what is a? A. So a was. So am was argument over a of this sign okay, minus beta h xi a. Right? Yeah. So not just like that. The sign is plus one minus one. I will just fit my a bar and beta to match the sign. Yeah. This is all it is. Okay. Once you've done that, okay, and now how do you find the row? How do the line search now? Let's see. So rho n is argmin over rho. So now the loss is this absolute value. So I see how much I'm suffering. I'm suffering is y minus 1 xi minus rho h xi am. Yeah. So at the MS step, this is how much I would suffer. And yeah, and there's actually a nice way to find this. So this is like a weighted median with the appropriate weights. So how? Because I could rewrite this as yi minus, so I can just divide by this weight h. And multiply by it. Right? Yeah, and now this is like a weight. So, so essentially these are my points now. And each point has a weight. And I want to find the number row which just kind of in the middle of all these points. I'm weighting them up. So it's a weighted median. Great. So okay, so yeah, that's what it looks like. Good. Okay. Okay, yeah. So the relatively easier examples are over. Now let's get to the tough one. It's called the regression trees. Yeah. So this is the reason why I did all this to get to this point. So okay. So now we're looking at a particular base learner. So H is A bar, which looks like the following. So this is a it's a rooted tree. And maybe you've all seen this before at some point, but have you seen this before? What this tree thing is? Okay, so the idea is that you let me first write down the final form and then I'll say how you get to it. So your final structure looks something like this. So your function h looks like, so h of x, and this a bar has a following form. So it divides the Euclidean space into regions. So a bar consists of bj and regions rj. So for every region there's an output bj. So this is an output, and there's a region for which it is the output. And the space is partitioned into regions. So rd is partitioned into rj. The capital J regions. So a bar has this form, and h of x a bar looks like capital J bj indicator 6 in rj. And where does the tree come from? So tree comes from the way these regions are defined. So regions are defined by a splitting tree.
Space is split into these two steps and break this one into those two.
Yeah, exactly. Yeah, so you pick a variable and you put some condition on this variable. Some condition. on the variable. Okay. And if this condition value should true, if you take the left path, if it's false, you take the right path. Then pick another variable and condition on that variable. Okay. Condition on another variable. Then you do the same thing. Yeah, and at the leaves of this tree, you will end up with regions. That's all it is. Yeah, and now you can probably appreciate that optimizing over these parameters is going to be very hard. Because how will you know where to split? Yeah, so trying to change on that is, it's not easy to think about. Okay, anyway, so but now let's see what it looks like. Okay. So okay, so now what is my update now? So fmx is fm minus 1x plus this update rho m changing from 1 to j. So for every region, I have a output bj if my x lies in that region. And at the ms step, let's call it rj. Okay. Okay, so let's see. So how would you find these? Okay, so suppose someone gave you these regions. So suppose regions were given to you. Yeah. Then how would you have founded the BGMs? Then BGM is not very hard.
Average of.
Yeah, exactly. Yeah.
Average of the points which are falling in that area.
Yeah, precisely. Yeah. So say average.
Average of the yi such that xi belongs to that.
Yeah. I mean, not y, but the gradient thingy.
Yeah, the gradient.
Minus gm.
Yeah.
Yeah, so then this is what you would do. Yeah, and you would find the rho m by a line search. Find rho m by line search. Okay. Yeah. So I guess then the only real question is that how do you find regions? How do you do this part? Okay. Yeah, so this is not straightforward, as you can imagine. So yeah, so this we'll do next time. So so because this really requires you to understand the trees.
You find the most differential variable and
Yeah. Okay, that's what we'll do. So, but this is like this is the part which is non-trivial. Yeah. But the point is that this part doesn't require you to know about boosting. This is just about trees. You need to be able to fit trees to data. If you can do that, then you can do this. So yeah.
I guess that's what this boosting is doing. This optimization over your you have split it and I mean, so the other thing that I was suggesting was directly taking partial derivatives using general. So by doing this other than the projection way, you said that okay, you can optimize over the edges whatever way you want. You don't need to necessarily rely on taking partial derivatives and so what I mean to say is that here if you have some edges. And in the steps where you want to find the A or the row, using like such. If you at that point to partial derivatives, you will get say similar thing to what you would have gotten if you directly took use Django to get partial derivative with respect to parameters.
Okay, I see what you mean.
So this way you have split the thing and said that, okay, this one you do it this way, this one you can do it this way.
Sure, yeah, exactly. Yeah, and here maybe partial derivative is not the best way.
Yeah.
So you say you can do some other fancy way you like. Exactly. Okay. So yeah, I think I want to I think I should stop here. So yeah, I think it went faster than expected. So yeah. Anyway, so yeah, the only thing left is that I'm not told you how to optimize how to solve a one tree. But that's nothing to boosting. That's
That is just very, you do nothing, but it's like you just do partitioning.
yeah. So you do some typically people do some greedy algorithm.
Yeah.
But okay, last minute early, so it's good. Yeah. So next time I will give some more fancy versions of this. This is like the basic gradient boost. But now the people have come up with all kinds of more clever and more efficient. Yeah. I'll cover some of this. And then I'll do like an overview optimization. Yeah, not only industry.